address in that minor group or major group. I'll show you that again in a minute. Okay, so now the second group. The second type are called zinc fingers. We've all heard of zinc fingers. Zinc fingers are structures. They define a structure that's formed in a protein sequence when that protein interacts with zinc. And it's generally, it can either be two cysteines and two histidines that interact with zinc or that bind to zinc, forming this structure, the finger structure, and that depends, of course, on where these residues occur along the amino acid sequence. It can also occur there can be four cysteines that do this, they coordinate that zinc. But in all cases, they create this finger. And here's another picture that shows all four of these regions, and it forms this helix here. The binding forms this helix, and that helix actually interacts once again in the major groove of the protein. So here's just some sequences showing you what zinc fingers look like. There's essentially what a zinc finger doing is it's creating the finger that interacts in the DNA. This shows you some can be all cysteine resins. And it shows you in the DNA sequence. So you have the conserved cysteines, right? These two cysteines are these two cysteines, these two are these two over here, and then the loop of the finger is what occurs in between. So the orientation of these, the distribution of these is very important. You can see here's a larger segment, there's a larger distance there. Here's these two cysteines, those two cysteines. So they form these finger elements. When they do that, essentially the zinc fingers themselves, right? This is the region of the zinc finger in here. This is where the zinc fingers form. And those zinc fingers are DNA binding elements. Once again, this is a common structure, that's found in many transcription factors. This is more common in eukaryotes. It's rare in a prokaryote, but it's very common in eukaryotes. And you can see what happens is when this region here, this is the DNA binding region, right? It then affects this transactivation, and this is the region that activates the gene. In other words, this is a protein. This region here is a transcription factor. This region binds to the DNA, and then these two regions here are involved in other things. This is one that actually activates transcription, and I'll show you how that occurs in a little bit. Region down here, right, binds hormones is involved in dimerization of form. Remember we said these work as dimers. I'll show you that dimerization region again. And there can also be transactivation things on both sides. So how do these guys bind DNA? This is a picture once again. And it shows you this is that helix that forms around the zinc. And those helix address that major groove. And this picture it's kind of hard to draw this cartoon. But this guy here is in the major groove that's going. This guy is in this major groove that we can see between those two helices. And this one is actually in that back groove where this helix and this helix are. In other words, the zinc fingers go on the opposite side of the DNA strand. So one binds like this, and then like this, and then like this, and then like this. And there's multiples. This particular protein had two zinc fingers, and many transcription factors do. Some of them have many more. They have 3, 4, all the way up to 7. And obviously, if you have the more zinc fingers you have that are where that helix is addressing this groove, the greater the specificity. So that you can have a transcription factor with multiple fingers. They have to address that DNA over and over again, and it gives huge specificity, which is why zinc fingers are much more common in eukaryote cells. Right? Prokaryotes have a couple thousand genes to worry about, 10,000 maybe at the most. They don't express many of those. Eukaryotes, 10,000, 25, 22 to 25,000 genes. So transcription factors have to have much more specificity. Also DNA size, right? In prokaryotes, the DNA is 10 of what it is in yeast, the smallest eukaryote gene. Okay, so this shows you the third type of structure. So we've talked about helix per helix, zinc fingers, and the third type is called leucine zippers. Leucine zippers are really kind of fun. Essentially, the proteins, these are the DNA sequence, or the amino acid sequences of many proteins. All of these are transcription factors. Jun and phos are, of course, eukaryotic. GC and Cor is in yeast. Krebs is eukaryotic. I don't see a prokaryotic one up there. CR is eukaryotic. So most of these occur in eukaryotic cells. I'm not even sure if there is every seventh amino acid, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So every seventh amino acid. Why is that important, every seventh amino acid? You all remember? I'm sure Dr. Glover told you about it. Somebody else. The turn of one turn of the alpha helix, exactly. The other region up here, this is a region here which is described, it's called, it has two basic regions, basic region 1 and basic region 2. And you can see that the basic regions have these basic amino acids, so they're charged, right? Lysine and arginine and arginine and lysine and so forth. So they're basic. There's two basic regions up here. Why are basic amino acids important? What's the charge of basic amino acids? Positively charged. So where are those amino acids going to interact? These are DNA binding proteins, right? So these positively binding proteins interact within the group within the DNA, right? Negatively charged DNA. So here's a picture of this thing. Here's the first thing that someone mentioned, and this shows you the alpha helix. And it shows you, when you do that, you generate these leucines. So here are all the leucines. And this creates a helix that we call an amphipathic helix. Have you used that word before? Have we used that word? Amphipathic helix is the helix that has an amphipathic helix is one that is different on each side, differently charged, differently something. In this case, you can see in this particular helix, it forms in the leucine zipper proteins. If you look down here, there's a lot of large asp, blue asp, a lot of charged amino acids, whereas up here, the leucines that line up across the top of that helix are all hydrophobic residues. So this is an amphipathic helix that's hydrophobic on one side and charged on the other side. And when people first saw this, right, when they first saw this structure, they said, whoa, that's going to be that's the forms the helix that interacts with the DNA. We knew about helix, term helix, we knew about the helix on the zinc fingers. But it turns out it's not. In fact, what that leucine helix does, this forms is the form of dimers. It's important for dimerization. So this leucine, repeated leucines, we call the leucine zipper. And the reason we do is that in regions there between the two proteins. So this is one of those amphipathic helices with leucines all on one side. And there's another one all on one side. And those hydrophobic residues, which are lined up with each other, every seventh amino acid just zip together to form a dimer. So they dimerize. So now we have these dimerized molecules, right? Second thing is that we have these basic regions here. And the basic regions contact the DNA surface. And why do we have two basic regions? Why is there not just one basic region? I don't think I have a picture of that. But I guess I don't. But if you look, actually, this picture here sort of describes it. This is showing. This is the dimerization. These are the leucines. It would be all leucines on each side of this thing dimerizing. And you can see these are going in the major groove. There's one major groove there, which is going right up there. There's another major groove this way, with the DNA going right in. And essentially, this shows you that helix being pretty rigid like that. And that's what the base actually does, is what the two basic regions. If you look at these basic regions here, right, they're two basic regions, and they're actually the helix. So the basic regions are in a helix. This is a helical forming region. It's forming a helix, right? But does anybody know what a helix breaker is? There are certain amino acids where if you have a helix and then you have a particular amino acid, it breaks the helix, right? And one of those is alanine. This double alanine, this region right here is a helix breaker. And that's why it creates basic region 1 and basic region 2. This basic region, this basic region. So this is in a helix and this is in a helix, and there's a little break in between. And what that does is it allows those two helices to bend. Rather than in a straight line, as in that one part, it's able to bend some, right? This shows it a little better here. Whoop, there you go. This shows it a little better. You can see how this would bend right there. And as it does bend like that, it kind of wraps around the DNA in the major groove. Rather than just sitting straight, it actually wraps right around. So both of these regions can interact with the DNA. Now what this cartoon doesn't show you very well And I don't even think the table shows you very well, it doesn't tell you. It doesn't, but you notice this is not, this region, these sequences are not right at the end, right? They're not, they talk about the amino terminal end, okay, this shows you, whoops, this shows you, here's these two helices, and there's the amino terminal and the carboxy. So the leucine zippers are here. But what they don't show you clearly is that these regions here, look at the amino acid numbers, they're really not right there at the amino terminal. In other words, they're not to scale. There's a lot of amino acids out to the front. These amino acids in the basic region are the regions that actually bind to the DNA. So what are they doing before they bind to the DNA? These are DNA recognition parts of the protein, right? So this region of this transcription factor is dimerizing it. This region, these basic regions, are recognizing the DNA. What are they recognizing? Some enhancer element, some element in the DNA, right? An enhancer element is the DNA. This region is what's recognizing it. Look at all the all these charged resonance, right? They're hydrogen bonding with the DNA, and they're recognizing that DNA sequence. This region up here, really, which isn't labeled, is where the transactivation domain is. Sometimes it's down here, not in these proteins, but in other proteins. In these proteins, it's up in the front end like that. So essentially, this dimerizes it. This recognizes the sequence. And it's something in this transactivation region which affects the DNA and causes it to be transcriptionally more active. So it actually either maybe melts the DNA helix a little, binds with the DNA, binds with the histone or something. Those are the transactivation regions. And remember, this guy here shows you that these